All right, so we just talked about circular points, didn't we? If I remember correctly, yes? Okay, so let's review very quickly circular points, because that's a very important way to define the projective space. So circular points, remember, circular points are solutions to our equation of a circle. The equation of a circle, of course, you remember from 5460, it's this one here, right? Where x, y, w are the homogeneous coordinates of the circle, right? So x, y, w, the homogeneous coordinates of the circle. Okay? And AB here, define anyone? AB1 in homogeneous coordinates, right? AB1 defines what? What is it? The center, very good, right? So define its center. And then R, obviously, it's the radius of that circle. Okay, perfect. And two solutions to this equation right here we saw is 1 plus or minus I, where I is the square root of -1, 0, right? So these are two classical solutions, and these 2 points are called the circular points. Okay? Very important points. And these circular points are on a very special line. Which line they are on? At infinity, yes. Why? How do you know that? Because the last component is 0, and that in homogeneous coordinates is defines a line at infinity, right? Okay, perfect, perfect. Okay, so with that, I want to define the dual of the circular points. Now remember to review the dual and this dual theorem. Remember all these things that we saw, that if we had points and lines, we could interchange them in the equations, right? And what was the dual of the other? Remember that? So this is very important to keep in mind from now on, because we're going to be using this constantly today. So the circular points, let me define them as capital I and capital J, are these two, -1, 0. Okay? These points are fixed, or if you want, invariant to any orientation preserving similarity transformation, right? So they are invariant to HS, I think we called it, right? To similarity transformation. So what that means is that if I have an I here, which is equal to I, this I here times some similarity transformation, what's this equal to? Well, this is equal to, this is S times the cosine of the angle minus S times the sine of the angle, S times the sine of the angle, and S times the cosine of the angle, Tx, Ty, 0, 0, 1, right? This is HS, and I here is 1, I is 0. And what's this equal to? This, I can rewrite this equation here. This is a rotation in the complex domain, right? This one here, which I can write as e to the power of negative I theta, right, times the scalar. So this is S E I theta times 1 I 0, which is, of course, the same as I, because it's like doing nothing, right? It's a circle, so it really doesn't matter how I rotate this. This is the same solution, right? OK, so you see that this one is equal to this, right? Perfect. So this fact is very important for us because it can be used to recover the 3D shape of an object by identifying specifically that H that keeps the circular points fixed, right? So if I'm working in the projective space and I want to recover the 3D shape of an object, I need to find an H, right, the matrix that I'm interested in, that preserves the circular points. And that gives me a similarity transformation, which is the world I live in, right? In my world, I live in the Euclidean space, and I want to recover my shape in the Euclidean space, and I want to do that, and therefore I want to make sure, that that projection matrix that defines my space, it's a similarity transformation, right? Out to a scale and a rotation. That's fine. I don't care if I recover that shape or this shape or this shape, right? So rotation and a scale, not important to me, but up to that similarity transformation, I want to recover that shape correctly in the Euclidean space, okay? All right. Also note that the circular points are given in a space of 2 dimensions, given by 2 orthogonal basis vectors, because I can rewrite I as 1, 0, 0 plus I 0, 1, 0, right? Is that true? Can I rewrite it like this? Same thing, right? And these are my basis vectors, right? And they are orthogonal to one another, right? So I, capital I, is defined in a 2-dimensional space, so it's capital J, which would be 1, 0, 0 transpose minus I 0, 1, 0, right? Okay, any questions? So we can also define the conic dual, and the conic dual, the dual of the conic is the conic. I'd say the conic is dual to the circular points, which mathematically I'm going to write as IJ transpose plus JI transpose, okay? And thus, I'm going to define it as my conic, okay? Or the dual, rather. And I'm going to call this C infinity because this is on the plane at infinity, or the line at infinity, the plane at infinity. We'll talk about this more later. Okay, anyone can tell me what's the rank of that conic? I and J are given in what space? Come on, anyone? What is it? I and J are given in a what space? In a two-dimensional space. Yes? So what is the rank of the conic then? 2, right? I mean, it's not a tricky question. Great. Perfect. Right? That's it. So it's degenerate, right? There is a 1 eigenvector that's associated to a 0 eigenvalue. So In fact, if you will, I can write. Can you all see here if I write here? No? Okay. So I can write C infinite. It's equal to 1I0, 1 minus I0 plus 1I0, 1I0, which is the same as 1, 0, 0, 0, 1, 0, 0, 0, 0, right? Right? So there is, this is only rank 2. And of course, there's rank 2 is given by this space that is given by the circular points, right? So you can, the circular points define that conic, and that conic defines the circular points. Correct? Okay. So far, so good? Question?
The minus on the vertical vector.
Yes. Yes. Thank you. Yes. Good eye.
Is it on, should be on the other one, right?
Did I do it? Oh, sorry. Yes. Which I said I is the positive or the negative. J is the negative, right? So this one. There we go. Good. Excellent. Now, remember also that we had, so recall that we had x prime equals hsx, which is nothing else than x transform with a similarity transformation, right? And the same applies to conics, obviously, right? Only that for conics, if I want to write this conic transform with a similarity transformation, then I need to multiply my conic on both sides, of course, right? And a transpose, right? And because this conic is defined by the singular points, and the singular points are invariant to any rotation and a scalar, right? This is going to be equal to the same conic, right? Makes sense? So the conic dual is invariant to any similarity transformation as well. So what all this means, so hence, is that conic dual has all the information that is needed to recover the metric of our image up to a similarity transformation, right? Up to scale and rotation. So remember that we had that particular equation where we can decompose our conic, this one here, into 3 different products. One we called P, A, and S for the similarity, the affine, and the projective transformations. Remember that? And now if I have this, this is equal to, what's this equal to? This is equal to HP HA now times HS, my conic dual, times HS transpose times HA transpose HP transpose. Am I right? Is that so far so good? And we know that this is the same as doing nothing, right? And therefore, I can just eliminate that part here. And let me continue over here. So this, I can rewrite it as HP, HA times my conic dual, HA transpose HP transpose. And this, I can rewrite it as, remember what we had given, K, right? Where K is the affine transformation that can define my affine camera, right? The parameters of my camera. And then here, I'm going to have V transpose K, K transpose, K, K transpose. K is a matrix, V is a vector. V transpose K, K transpose V. And now remember that K defines, it's a matrix because it defines the affine transformation. V is a projective vector, right? On our generic matrix, remember that we had K, V, our translation, and a 1, right? And when we decompose it, the HP projection was left with just this one vector here, right? Okay. Excellent. So let's see an example of this, how to apply this. This is really cool. We're getting into very interesting territory now. So I'm going to apply this to the recovery of Euclidean geometry from an affine solution. Okay. So I'm going to use any algorithm that we define in 5460 and recover an affine shape for an object or an affine camera or an affine anything that you want, right? And now I want to recover the Euclidean geometry of that affine solution. For example, affine structure from motion, right? Okay. So I'm going to start with 2 lines. Let L prime and M prime be 2 lines recover in our affine solution. Okay? So these are our solutions using, say, affine structure from motion or anything else. Okay? Now, the Euclidean counterparts, so these are affine. The Euclidean counterparts are L and M. Okay? And what do we know? We know that L and M are orthogonal to one another, for example, right? So we know that these are orthogonal. Okay? You can also use the fact that they may be parallel, but something that you know that you can compute in Euclidean geometry, but it's different in affine geometry, right? Okay, so that means that L1, L2, L3 prime times some transformation here and times M1, M2, M3 prime, right? If I apply a specific transformation here, this has to be equal to 0, right? Now, because this is in the defined space, this product, if that were the identity matrix, this product would not be 0 necessarily, right? It would only be 0 when we are in the Euclidean space, right? So I need to find an affine transformation here, A. Let me, in fact, call it as we did there, K transpose. And then 0, this is a vector of zeros, another vector of zeros, and a 1. And that has to be equal to 0. Okay? Now, what do we know? We know that L prime C infinity star, so the dual, times M prime, this has to be equal to what again? If this is the dual? 0. Very good, right? Okay. Therefore, we can take, so here I've assumed obviously that this V vector is 0 because I have an affine transformation. So let's see. So this matrix obviously is symmetric positive semi-definite, right? Has to be. It's an affine transformation. Okay. There are multiple solutions to this. Why don't I assume, well, it doesn't matter, right? I'm not going to assume anything. But there are multiple solutions to this, but this is a system of equations, right? And I'm going to get enough equations with just 2 pairs of lines, right? If I have 2 pairs of lines, I have enough equations to solve this, right? So I need at least 2 pairs of lines, and I can solve it with least squares, right? That's it. Yes, question?
The y should be 0.
Which one?
The second row and the second column.
Do you mean here?
Yes.
No, that's a 1. This is the generic transformation, right? Remember, this is like this transformation that we've always worked with, where there is like this, translation and a 1, right? This is a generic projective transformation. But here, because it's an affine, I'm assuming that this is 0, that there's no projective vector here, okay? Now, you could include a translation here, which we haven't, because our solution, we don't care if it's up to a translation, right? Whether I recover the shape here or here, it's irrelevant to me. Okay? So you can solve this with least squares. And that's it. That's how you actually solve these problems, right? Of recovering the Euclidean geometry from affine solutions, which is something that we couldn't see in 5460. Okay. Any other questions? Okay, so let's move on to quadrics. And this is now one of the most important topics we're going to see. Because it has really cool applications. Quadrics, so up to now, we've been working in P2, right? The projective space of 2 dimensions. Yes? Now, obviously, I want to work in P3, right? Which means that I'm working with planes. And for that, I'm going to need quadrics. So a plane in 3D space, right, can be written in homogeneous coordinates as pi equal pi 1, pi 2, pi 3, pi 4, right? And every point x on pi satisfies the equation pi transpose x equals 0. True? Right? So what I want to do is parameterize this in a way in matrix form such that I want to find a, so let me do this, with a matrix M, or let's say a 4×3 matrix, 4 by 3 matrix M that's going to be rank 3 because I want it to be rank 3. So it's going to be full rank on one of the 2 dimensions that it has. I could define M as, so this M, I'm going to define it as having P here, the component P that's going to define somehow my plane. We're going to get to that in a second. And then here an identity matrix. Okay. So here's going to be the identity matrix of 3 by 3. Okay. So I want to parameterize this with this such that pi transpose M is equal to 0, right? Same as this equation, right? Okay. So one way to do that is to define my matrix M one way to do that, my matrix M with P equals to negative pi 2 over pi 1, negative pi 3 over pi 1, and negative pi 4 over pi 1 transpose. Of course, if and only if pi 1 is different than 0, right? My pi 1 cannot be 0, otherwise I couldn't do that, right? Then I have to parameterize it some other way. Okay. And then I can define a quadric as the surface in P3, right? So then a quadric is is a surface in P3, the projective space of 3 dimensions, given by the equation x transpose q x equals 0, where Q is a 4 by 4 matrix with 9 degrees of freedom. And hence the number of points that I need to solve for this equation is 9, right? And at the minimum, 9 or more. Okay, and so this is a quadric. Remember actually 5460 that we talked about quadrics very briefly, but we never used them when we introduced the homogeneous coordinates. I don't know if you remember that way back. But now we're going to use them, right? Because we want to work in 3D space. And in particular, I want to define the plane at infinity. Now, the plane at infinity is equivalent to the line at infinity. Of course, the line at infinity, I define it in P2. Now, in P3, I'm going to define the plane at infinity, right? But same thing. It just happens that any plane, pi, is going to be pi 1, pi 2, pi 3, and not 1, 0, right? And any plane that has a 0 as its homogeneous coordinate, and it defines a plane at infinity. That's it. It's that simple, right? I mean, once you understand the projective space, which is very abstract and difficult to grasp. But once you grasp it, this is it. There are no secrets, right? Just put anything that has a 0 here defines the plane at infinity, which we can call pi infinity, right? Make it super clear. OK. So remember that in Cartesian coordinates, though, right? So this is in homogeneous coordinates. In Cartesian coordinates, we use the notation 0, 0, 0, 1, right? That might have been the confusion there, right? That would be the Cartesian coordinates of the plane at infinity, because that plane is anything that, when multiplied by it, it equals 0, right? In the Cartesian coordinates. Yes, makes sense? Okay. Okay, so any two planes are parallel if and only if, anyone can tell me? How do I know if two planes, pi 1 and pi 2, or pi and pi prime, are parallel to each other? If, go ahead. Well, yeah, but in the projective space, how do I know that? Because they meet or they cross where? Not L, not L, right? At the plane at infinity, right? Any two planes that cross at the plane at infinity are parallel planes. Remember that two lines that meet at the line at infinity are parallel lines? It's the same thing. Nothing's changed. Two planes that cross at the plane at infinity are parallel planes. Okay? If and only if they meet or cross at pi infinity. Okay? In the same way, remember, because of the duality that we have in the projective space, a line is parallel to a plane if and only if the two intersect at the plane at infinity. I can interchange the roles of my planes, my lines, right? And therefore, they also have to cross at the plane at infinity. In fact, everything that we have seen in P2 applies in P3, but just adding one dimension. And everything that we'll see in P3 applies to P4, and so on, right? Just keep adding one dimension. Additionally, note that if I have a plane, okay, let me see if you can come up with this. So imagine that this is my plane at infinity right here, okay? So far, so good. This is just an arbitrary plane, and I've decided that plane is a 1 at infinity, right? Okay? So in homogeneous coordinates, the last component of the plane is 0. And now I have another plane pi. That looks something like this, okay? And there is an intersection between the two, and that intersection defines this line. Anyone can guess what that line is using the knowledge that we have defined here? What is it? Correct, right? This, of course, it's the line at infinity for that plane, right? That's exactly what it is. Why? Because that line that it's on the plane at infinity has to have the last component 0 by definition, right? You see that? So two planes that cross at the plane at infinity have to share that line at infinity, right? But if they are not parallel, they don't have to. And then remember that from 5460, we actually saw this. If I have this plane, my ground here, my floor, and I take a picture with projective projection with a pinhole camera, right? I'm going to see a horizon at the end of that plane, right? in my image, in my 2D image. And that horizon is the line at infinity, right? Yes? But if I have another plane here, say it's length plane like this, that's going to give me another line at infinity, right? But all these lines at infinity are at the plane at infinity, right? OK, good. Isn't that cool when everything actually makes sense after seeing all this material? OK, the absolute conic I'm going to call it omega infinite, is a conic on pi infinite, okay, on the plane at infinity. So that particular conic has to satisfy, so I could say omega infinite satisfies satisfies two equations. x1 square, x2 square plus x3 square has to be equal to anyone if it's a conic. 0, right? And x4 square, well, it doesn't matter if it's a square or not. x4 has to be equal to 0 because it's at the plane at infinity, right? So, for example, this constraint here, you can write it as x1, x2, x3 times the identity matrix times x1, x2, x3 transpose equals 0, right? Which would identify a conic, right? Remember from the equations that we derived earlier, that is equal to the identity matrix, right? Now remember that the conic, right, in P2 was that ellipsoid, right, that defined that equation x transpose cx equals 0. Remember that equation that defined that conic? That defined all the x's, all the lines that are tangent to that conic. So the conic is defined by all the tangents, right? All the tangent lines to that ellipsoid. Remember that? We had a nice drawing. Now in P3, the conic is defined by all the planes that are tangent to it, right? It's the same thing. All the planes that gives an equation equal to 0, right? Okay, so quick result. It can be shown that the absolute conic is fixed under a similarity transformation. Okay. Maybe at this point, I'll leave this as an exercise for you to prove that. It's the same proof that we've been doing. And obviously, you have the solution in the handouts in Carmen. All right. Good. Also, we're not necessarily going to be using this, but remember that we can define a metric in any space. So we're going to find a metric of the projective space as the same metric that we've been using always. Remember that we can compute the cosine as, say that I want to compute, I know, let's say the points or the distance between two different points or two different planes. The same thing applies. It would be D1 transpose D1, right? But now I need to multiply this not by the identity matrix. If I multiply this by identity matrix, I'm in the Euclidean space, right? But because I'm in the projective space, I'm going to multiply it by the conic. So by omega infinite. And I'm going to divide this by the square of each of them. Oops, that should be D2. Sorry. And I'm going to divide this by D1 transpose I'm missing something here. My notes are, I don't think my notes are correct. Hold on a second. I know I'm missing something, and all right, I'll give you the solution because I want to make sure that I say something that is wrong. So I will check because we're not going to use this. It's not urgent. I will check and I'll give you the right solution, okay? Because my notes are wrong. I know they're wrong. And I just want to make sure that I give you the right one, okay? So let's move on. So the next one is the absolute dual conic. I'm sorry, it's actually called quadric. So remember that the absolute conic is given by two equations, these two equations that I have over there on your right-hand side. The dual of that conic that we have defined is a quadric in 3D space, and it is called the absolute dual quadric, and I'm going to notate it as Q infinite dual, okay? Now, again, remember that I can compute this with the planes tangent to my conic, right? So I have the conic, and all the planes that are tangent to that conic define the dual, right? So algebraically, I can write that this is equal to the identity matrix here, 0, 0, 0, okay? And this is rank deficient, right? Because there has to be a null space, right? The null space is precisely what defines my conic, right? Okay. So does the rank of my quadric has to be equal to 3, right? 4 by 4 matrix, therefore this is 3. So what is the plane of that defined by that quadric? So I have this quadric here, right? And now if I multiply this by a plane, there's a specific plane that's going to give me this equation equal to 0. Which plane is that going to be? The plane at infinity, right? Very good, because this is exactly the plane that is going to, it's a null space that defines the null space of that quadric. So, in fact, let me do a short parenthesis here. We're going to prove this in a second, but if P is the camera matrix, remember, P, the camera matrix, times Q dual times P, that has to be equal to my conic in 2D space, right? So if I have my projective matrix, the camera matrix, P, that projects from 3D to 2D, right, or from 4D to 3D, if I'm in the projective, then that quadric, the absolute dual quadric, is going to project onto the dual of the conic, right, that we had defined earlier when we were working in P2, right? Okay, just a parenthesis. We're going to prove this in a second. Everything that we've said about P2 applies to P3. So obviously, this quadric is fixed under any projective transformation H, if and only if H equals a similarity transformation, right? So this is fixed under HS, okay? Any similarity transformation. Okay, so let's use this for camera calibration. And in particular, I'm interested in self-calibration. So I'm interested in an algorithm that can calibrate itself, okay? Given a certain number of points or a certain number of lines, I want the algorithm to calibrate itself, right? Remember in 5460 that we defined this very complicated algorithm where you have to actually put a lot of stickers in the world, right, that are at specific distances and locations because you need to be able to recover all the parameters of the camera. Well, you can actually define self-calibrating algorithms from point correspondences. Let's see how we can do that. To do that, recall that the line L that is tangent to my conic equals this to 0, right? Satisfies this equation, right? It's all the L's that satisfy this equation define my conic, right? This is the dual, basically. So in fact, these lines back project. They back project to, so if I do P transpose L to my plane pi, where P again is the camera matrix, right, that I'm interested in. So this means that I can also write pi transform Q pi, right, equals 0, same thing as before. And we know that this is equal to what? This is equal to L transpose P times Q dual P transpose L, which is equal to L transpose C dual L, which is 0, right? Yep. So if we let W dual be defined by B transpose Q infinity P, where here W dual is the two-dimensional dual image of the absolute conic, okay? So the image of the absolute conic. Remember, the absolute conic is a three-dimensional conic, right? And if I project it with my camera projection matrix, I get the two-dimensional image of that absolute conic, right? I mean, think about the same thing. This is easier than it seems, right? Think about the line at infinity, right? When I take a picture of the three-dimensional world, then I take the line at infinity as my horizon, right? I swear these things are just so funny. Who knows why they understood. What was I? I lost my train of thought. So when I take a picture, I see the line at infinity, right? And that's the same thing. I take a picture of the 3D conic, and what do I see? I see the 2D projection of that conic, right? Okay, so this W is the projection of the conic. So this is K transpose, right? That was the conic C that we were interested in, right? Yeah. Okay. So what we are going to do now, we're going to decompose our quadric, right? Our absolute dual quadric, Q infinite dual. We're going to decompose it as a matrix H, a matrix I tilde, and a matrix H transpose, same matrix, where I tilde is equal, this is where, equal to the identity matrix of 3 by 3, and then 0, 0, and 0. Okay? So it's a rank efficient identity matrix. So it's a diagonal matrix of 1, 1, 1, 0 in the diagonal, and 0 everywhere else in the off diagonal. And H here, well, in fact, H inverse is a three-dimensional homography, right? That we defined in our last lecture. That maps, so where H inverse is a 3D homography that maps the projective space to the Euclidean space. Okay? And we can use the same tricks that we have been using until now to find that projection, right? Which is nothing else than an eigenvalue decomposition. So let's see the algorithm then. With all that information, let's define the algorithm. Okay. So let's put all this in an algorithm form. A, first, compute the projective reconstruction using a set of views given by the camera matrices Pi and a set of point correspondences Xj, right? So given my Pi's, these are my projective camera models, right? The 4x4 matrices that define my cameras. And my points Xj's, right? I'm going to obtain my Xij point correspondences, right? And then with this, I can use my algorithm to recover any to recover any solution that I need to recover, right? Okay. So this is A. B, compute Wi or omega I, where this is defined by this, right? The projection of my quadric, and therefore this is now Pi transpose Pi Q infinite dual Pi transpose, right? That makes sense. Now, pi, remember what I said here, right? Pi q p, that has to be equal to 0, right? That's what we have here, right? This has to be equal to 0. So you can use that system of equations to solve for q, right? Yes? So we can solve this using least squares, right? And these equations are linear equations, so they're easy to solve. And let's see, C, we decompose our quadric as H I tilde H transpose. And finally, I have recovered H, which gives me the projection of the camera. And where do I have this? Oh, here. I have H that defines the camera parameters, right? That project to the Euclidean space. So the points in Euclidean space are going to be given by xj. Let me put a E, capital E here as a superscript to identify that this is now in the Euclidean. H inverse xj, and the cameras are going to be given by the pi's in the Euclidean space as pj's times h, right? Yes? Is that clear up to here? Are these steps clear based on everything we've seen? I need a nod or a no. Yeah? Okay, let's review. So we have our cameras and we have our points, right? And the corresponding image points that we can compute, right? Point correspondences. That means that given this set of equations, I know how to solve for the parameters of my absolute dual quadric, right? And then once I have this, I can decompose this for H, right? And once I have H, I can recover the Euclidean geometry of X and the Euclidean geometry of my camera parameters, right? Yes? Because H is the equation, the transformation that forces me to be in the Euclidean space, right? Now, there is a way to improve this result, as we did in 5460, because this is the linear solution. We can extend this to nonlinear with nonlinear least squares, for example, with, remember what's called bundle adjustment. So you can improve with nonlinear least squares. For example, I could minimize the equation Ki transpose. Remember, Ki transpose, nothing else than my projection, minus what I have recovered here, which would be Pi Q infinite dual Pi transpose, right? And you need a norm for this. Usually people will use the Frobenius norm for matrices because it's the easiest to compute, right? So there are other solutions that people have discussed over the years, and you will see those come all the time. All the solutions that have been defined use the techniques that we have introduced here in class, right? There are very few other techniques that we have not talked about. So all the techniques are, or you should already be familiar with all the techniques. But I will mention very briefly, we're not going to go through all the derivations again because of lack of time, but I'll mention briefly two other things that I think are relevant or important to mention. So another solution to self-calibrate the cameras is to actually use this solution here that we have derived earlier. So we can use the fact that we can compute first. So first, so this is another solution. Okay. First, compute omega I dual, which remember is equal to pi the quadric, the dual, the absolute dual of the quadric, pi transpose, and then get ki from this, because you know that this is equal to ki transpose, right? So from this equation, you can get the ki as well. And to do that, there is a factorization rather that you can use, which is called the Cholesky factorization. Cholesky, excuse me, factorization. That allows you to do that. Another solution that you'll see quite often in the literature is given by the use of the fundamental matrix. You might remember the fundamental matrix. Capital F. You could actually show it's actually straightforward, right? Based on everything that we have seen thus far, that the fundamental matrix F times the conic, the dual of the conic, times F transpose has to be equal to 0, which is actually the same as taking the skew-symmetric matrix of the epipoles. So the epipole E X, I'm going to write it like this, C dual E X. And actually, here, to be precise, I should probably add, okay, let me add this. I should probably add here H, which is a some similarity transformation or some affine transformation. Actually, let's not. Okay, let's skip that. Doesn't matter. But the fact is that, as we have done before, F, the fundamental matrix, remember, that defines my multi-view geometry when I have more than one camera, defines the camera parameters and all the epipolar geometry, right? Is also given by the equation of the conic, right? So if you write this system of equations, you can also solve it with least squares and solve for self-calibration. Okay? Yeah, I don't want to give more details because it's not necessary. But just to give you an idea that you can use these equations right here with the absolute dual quadric or the conic, right, the dual of the conic, to solve for system of equations. And with that, once you have a system of equations, you can solve for all the transformations that we have seen in 5460 but in a much, much, much more elegant and efficient way. Okay? All right, any questions? So this is all I have about the projective space. We have just one more topic before the midterm. This is image segmentation. Okay? All right, I'll see you Thursday.